The research line of chemical artificial intelligence sprouts from natural computing and is trying to answer the following heuristic questions. Which biological intelligence competencies can be mimicked through inanimate chemical systems in wetware in a liquid solutions, which is the characteristic phase of life? Traditionally, artificial intelligence is developed through two strategies. One relies on software running on current electronic computers or special-purpose hardware. Such software either reproduces the human thinking process when it is a flow of rigorous logical operations, or it mimics some structural and functional features of neural networks to learn how to perform tasks from data, or it mimics some other natural rational phenomena, for instance, biological evolution, in the well-known evolutionary algorithms. Another traditional strategy to develop AI relies on reverse engineering neurons and their networks in hardware for neuroprosthesis or to design brain-like computing machines, revolutionizing the von Neumann architectures of current electronic computers. Recently, a brand new strategy to develop AI has been proposed. It's the so-called chemical AI. It relies on molecules and macromolecules that operate as if they were hardware, but they are dissolved in liquid solutions where phenomena such as chemical reactions, diffusion, migration, advection, convection, and chemical waves can occur, and these phenomena operate as if they were software. In other words, the hardware and software of conventional AI are merged in the wetware of reactive chemical solutions, maintained in out-of-equilibrium conditions. In this slide, I report the knowledge map of chemical AI, that is a three-dimensional graph projected on a plane. Along the x-axis, we have the chi-domains, that are molecular and supramolecular chemistry, system chemistry, and multiscale chemistry. With multiscale chemistry, I refer to all those chemical systems that manifest self-organization at different spatial scales and multi-level causality when appropriate macroscopic thermodynamic forces are applied. Multiscale chemistry is required to mimic some structural and functional performances of multicellular biological organisms that exhibit multiscale competencies. In the knowledge map of Chi, along the y-axis, we have the Chi paradigms that are biosensors, brains, and effectors. And finally, in the third dimensions, represented by the saturation degree of the green color, we have the biological intelligent competencies that range from sensing to perceiving, from computing to planning, from working to acting. Some of these competencies have already been implemented. They are indicated in black. Some others have not implemented yet. They are indicated in white. Probably they will be implemented through a further development of multiscale chemistry, or probably they will not be implemented at all. Because if we think well about the competencies in black and those in white, we see that they are separated by a still unknown concept, that of consciousness. An ambitious goal of chemical AI is the development of chemical robotics. A chemical robot is envisioned as a confined complex molecular assembly that reacts autonomously to its environment. Because it has sensors collecting data about the environment and internal state of the robot, it has artificial neural networks to process the sensory data, making decisions and triggering the actions of the effector modules that can affect the surrounding environment and internal state of the robot. The intelligent activities of a chemical robot should be sustained by an appropriate metabolic model. Chemical robots should be easily miniaturized in order to be implanted in living beings and interplay with the cells and organelles to perform biomedical actions. In other words, the prototypes for these chemical robots are lymphocytes, the cells of the immune system. But at the same time, we might think of deploying chemical robots in the environment to fight pollutions and face problems related to energy and food supplies, as enticingly alleged by the futurist Kurzweil. In these latter cases, the prototypes for the chemical robots are the microorganisms. The development of chemical AI might have a curious side effect. It will probably assist human efforts to unveil the mysterious event of the appearance of life on Earth. That staggering event occurred roughly 4 billion years ago, has been described as a phase transition from a completely abiotic world to a world where the first complex chemical systems capable of exploiting matter and energy to encode, collect, store, process, and send information to pursue goals somehow pop up.